Good morning, everyone. My name is Chirantan Jain, and I am a co-committee member of IET-VIT. I am pleased to see the enthusiasm of the audience and would like to welcome you all to the workshop of Step into AI/ML, the ins and outs of ChatGPT. We are glad to introduce our speaker of today's workshop, Mr. Abhilash Majumder. He is currently a senior supercomputing HPC engineer at Intel, enabling next-generation GPUs, XPUs for exascale computing, deep learning of very large models spanning vision multimodal contexts. He was a research scientist for Morgan Stanley and a collaborator for Imperial College London for fine tuning and building large language models. Now, he's also an author, mentor, and have provided deep learning, quantum deep learning related sessions at Python conferences globally. Sir, we are grateful to have you today. The platform is all yours.
Yeah, hi everyone. It's really great to see, right, and interact with everyone. As Chirantan has mentioned, by you already know, I'm part of Intel, right? My current work spans leveraging and optimizing large-scale language models, vision models, and multimodal models for different of our clients, right? ChatGPT is actually one of the major breakthroughs in large language models, particularly in supervised training and supervised fine tuning. And it has been quite a journey, like going from GPT 1, 2, 3, 3.5, and then up to your the ChatGPT versions. In this case, today we'll be understanding more about what ChatGPT is and how it is taking the world by storm and why everyone is so hyped about it. The thing about this chat gpt is it is very much a huge language model, right? It requires huge amount of compute resources and whatnot. And OpenAI has done a brilliant job to give us an api that we can use, everyone can use, right? To leverage the power of generative modeling. But there are different concepts behind this chat gpt, right? So today we are going to cover what chat gpt is and how interesting the different kind of internal layers, internal mechanisms, and different approaches are present to, have been used to train this beautiful model. So I'll be sharing my screen just to give a brief walkthrough of the presentation that I created, and then we can have a little bit of code review because I'm a follower of Linus, right? And without code, it's all haywire, right? So we are going to go through a little bit of code to see how and what ChatGPT is. As far as I know, they have not open sourced the code yet, in terms of because of the potential, I would say, drawbacks of it being misused. So this AI powered chat gpt is quite powerful, and the amount of resources and the knowledge base that it was trained on, although chat gpt says it is trained up till 2021, but it has still updating its knowledge base in the recent years. So it is a very powerful language model with lots of resources and knowledge bases available at its exposure. And and in this case, we are just going to see a minimalist kind of implementation which I created, but that is still in progress since it is a very big model, right? So let's start with the presentation and we'll go forward from there. So I hope you can see the screen, right? So we are going to understand what ChatGPT is. ChatGPT, the word GPT, if you can see my screen, right? I hope you can see my screen. So GPT means generative pre-training. Now, in the case of NLP, right? NLP and large language models, there has been an advent of something called as a transformer model, right? For those who are unaware of the transformer model, it looks something like this. I have a repo where you can see, right? Um, so the transformer model looks something like this. Okay. Now, this is a very complex machine learning model. Now, those who are not aware of what a machine learning model is, let me just give you a brief info. A model, as of now, is not just a black box, right? It will not automatically give you predicted results based upon your inputs. You need to train that particular model. You need to train that particular black box, so as to quote. But that black box has different intermediate layers, right? Different kind of mathematical computations are being done. And in the case and in the world of deep learning, right, any kind of deep learning that you see, let's say non-quantum deep learning based, there is always a kind of a variant of matrix multiplications, rank reordering, and different versions of linear algebra being applied. So all of these layers are present inside this black box, which we are trying to train, right? Just like training an infant or training a pet, right, to do a correct thing. So it is just like that. So in this case, we have different kind of layers, right? Those layers are nothing but certain mathematical functions. The function can be as simple as adding two numbers, or multiplying two numbers. But in the case of machine learning, right, in the case of deep learning, we have nonlinear functions. Nonlinear functions means these functions can be either exponential, these functions can be polynomial and whatnot in the real domain. Now, in this case, we have something called as a transformer model, which is a very big model, right? And what this model does is, as you increase the strength, by strength I mean the number of layers, the potential matrix computation capability of your internal layers, right? Your model can, understand and try to replicate and try to predict correct answers given any context, right? So the first step is to do something called as a supervised training. In the lingo of transformers, this is known as pre-training. So we have a kind of a input sample and an output sample, right? We pass in the input and we validate it against the output. This is known as the training phase. Okay, the training phase in a nutshell comprises of two factors. One is your forward and your backward. Forward means that, let's say you provide an input to your model. Let's say your model is a simple addition function, f of y is equal to f of a plus b, for example. Now that addition, you need two inputs, a and b, right? And it gives a, let's say, an incorrect output. Let's say 1 plus 3 gives you a value of, let's say, 3.5, for example. But your correct output is your 4. So the difference, that is your delta, that is zero point 0.5, is your error. So the main, I would say, point of having the supervised pre-training is to reduce that error. And how you reduce that error is by use of different functions known as loss functions. Okay, so and the machine learning model always tries to optimize these loss functions. Now, in the case of the transformer, right, the same thing happens. The same idea, it percolates through different layers, and you have different kind of mechanisms, right? You have the attention mechanism, which is a very fancy mathematical implementation, right? And you have something called as a feed-forward networks. Feed-forward networks are simple perceptrons. Perceptrons means, just like I told you, it's let's say a simple mathematical function, might be a polynomial function, let's say multiplying two vector matrices, or it can be using some activations or some nonlinear functions, right? So the feed-forward networks are the simplest form of neural networks. In the case, if you are familiar with PyTorch, TensorFlow, these are generally there are generally terms known as dense or MLPs, right? So these platforms also have lots of resources available for getting started with simple perceptrons, right? The attention mechanism is very much peculiar because it is a beautiful tool used to optimize large language model training. How it does that? Let's say you are training a baby to say a few words and to understand a few words. Now you have given a sentence, right, to an infant. He will try to split the words into smaller parts and try to understand each word in a particular context window, right? Let's say I like to eat ice cream. So the word, so the if you tell this to an infant, he will try to understand that. So let's say I is in the context of something. So I is the subject, is in context of certain predicates, right? Certain objects. So in this case, my object is ice cream. So in the context of ice cream, what is, how should I frame my answer? Like, let's say, what do you like to eat? And the baby and the infant understands these questions like, what do you want to eat? Each word broken down, right, to understand the context in as the global context. What do you? So what is the importance of the character, the word, the single word you in the entire context? What do you want to eat, right? So just a similar way, the attention mechanism does just that. So it takes one character, right? It takes certain tokens in the machine learning language, in the LLM language. We use that as tokens. So every token or a word is given a corresponding score, a probabilistic score, or an importance, right, or an importance weight in a particular context window, right? How that score is generated is based upon this mathematical functions called as attention. So there are different variants of attention, right? How we, if we want to take, let's say, a small chunks of your entire sentence, let's say break down your entire sentence into smaller chunks, let's say 2 words at a time or 3 words at a time, or you want to take the global context. So there can be global context, local context, right? And this is how you actually generate a kind of an importance sampling of your internal weights, of your internal tokens, weights of your internal tokens, right? And why this is important, because your model will then understand that given this context, this particular token has a greater weightage. So this is what a transformer network attention essentially does in a nutshell. Now, there are different mathematical formulations for doing, attention mechanisms. Uh, if you are familiar with, I have linked certain resources. This particular paper is what is interesting, and there is one person called as Jay Alamart who has written a beautiful blog on this, and you can check out his blog to understand more about how this attention mechanism works mathematically. There are certain tensors, mainly called as query key and value tensors, which are used for simple linear algebra matrix multiplication tasks to generate this importance sampling, right, of individual tokens. Now, whatever sampling we do with these individual tokens, we pass them to our simple feed-forward network. It can be any simple perceptron layer with a kind of nonlinear activation unit, right? And this particular block is known as your encoder block. This particular block of the transformer is known as an encoder block. And this big chunk of block is known as the decoder block. So essentially, you might see that the same stuff is present in both of them, right, with minor differences here and there. When you see these splits and these merges, right, this is nothing but concat operation and split operation. Concatenating means you are concatenating different attention results. Let's say attention result of a particular of 2 3 words in a particular sentence. You are concatenating with the attention scores of the next 2 3 words in a corresponding next sentence, and you concatenate the results. Now, why do we need to concatenate? Is because when you are analyzing a big context or a big corpus, let's say a paragraph or a book, for example, you not only need to have your local context, you also need to have your global context in place, so that your any kind of model that you want to build, right, transformer model you want to build, understands that and is trying and can try to replicate that. So these individual things that you see, softmax is kind of an activation, which exponential activation unit, which tries to give you a sample of outputs. So in deep learning, you generally have, in deep learning classification based, right? So you generally have two kinds of classifiers mainly. One is your binomial classifier, and the other one is multinomial classifier. Binomial, as the name says, you have only two labels, black and white, you want to classify it against. Multinomial implies a more range of labels, right, greater than two. So binomial is a special case of multinomial, right? And there are different loss functions to handle those. So in the lingo of frameworks, PyTorch and TensorFlow, these are known as cross entropies. You have categorical cross entropy, you have binary cross entropy, right? This entropy, or your this multinomial kind of labeling, right, uses an activation called as a softmax activation, okay, which is an exponential activation unit. The reason why we need this softmax is because each word, let's say you want to build a classifier. So if you want to build a classifier, right, you need to classify a sentence or a corpus, whether it's positive or negative in the simplest terms. You can use your softmax, or you can use your sigmoid as your activations unit. Sigmoid is best suited for binomials. So in this case, your outputs will give you different values. Okay, so let's say depending upon a corpus, it will classify it as positive or negative based upon all these internal computations that you see. Okay, so that but this is the actually the starting point of what transformers is. And after that, there have been many years, 2000 from 2016 17, right? There have been many years, and now we are having GPT, right? So there is a difference. This particular architecture that you see is the default architecture for encoder decoder dual type transformers, right? You might have heard about BERT. Those who are familiar with this type of lingo in large language models, you might have heard about BERT, quite famous. So this BERT language model only has this particular block, this encoder block stacked up to 12 or 24 times to give you a kind of a language model. BERT is not suitable for generating, so it is not capable of generating sequences. By not being capable, I mean that it has, due to its nature of its encoder layers, right? It will not be able to give, your sequences depending upon your input sequence. There are also different small, details here and there. The way how they tokenize from left to right, and your decoder pure models do it from right to left. But those are the nitty gritty details. But BERT is essentially used for any kind of, I would say, causal LM. So you will have, let's say, question answering. You will have, if you want to generate some tokens, right? You want to segregate certain tokens. Let's say you have the name of a place. Let's say I live in Delhi. So you want to segregate the name of Delhi as your entity, right? So though in those cases, right, these kind of things are called as discriminatory language models. So these discriminatory language models, BERT is the classic example of that. They are particularly extremely well in classifying stuff. But in the case of GPT, it is a separate class altogether. GPT also uses this same kind of architecture, but this block is not present in GPT. It uses the pure decoder stack in GPT. Okay, and the reason why is because the task of GPT is not to classify something. The task of GPT is to generate. That is why the name comes. That is why there is the name generative pre-training. That means based upon your previous inputs that you provide. Let's say you are giving a prompt, right? For example, um, let's say Mumbai is very hot at this time of the year. So based upon the input sample, right, your model, your autoregressive GPT model, is going to take that particular input, and it is going trying to generate sequences in the next few cycles, next few iterations. Okay, so this is how GPT is different. And for that to generate new sequences, you need a decoder pure network. You do not need an encoder network, because you are not classifying anything. You are not doing something to segregate certain things. You are just doing a kind of a generative workflow. How you generate, there are different kind of generative algorithms present, like the most common being the beam splits. So the beam algorithm actually splits your generative sequences or tokens based upon this weighted individual tokens from these attention mechanisms. Okay, so GPT architecture is similar to that. Now, if we go back to the slide, right? So we have just understood what the T means. T means GPT stands for generative pre-training, right? The T also means it is a transformer model. So the first thing is to understand that it is a transformer model, the architecture which we just saw. And GPT, G means generative, P means pre-training. So autoregressive models are something which takes an input, gives you an output based upon the weights of the relative weights of the input tokens. Okay, but there is a difference between the previous versions of GPT that we have, let's say 1, 2, and 3, to the latest one that we are studying now, that is ChatGPT. With this important tricky stuff, which is known as this particular guy over here, reinforcement learning. Now, this particular concept is very difficult to understand. Um, and before we go into the reinforcement learning part, right, we have to understand what do we mean by GPT 1, 2, and 3, because as a layman, I do not know what that means. So think of it like this way, like as you go up, like as a child, as an infant grows up, right, his knowledge base is going to increase. Like he's going to take up a lot more information from his outside environment, and he will have a lot more knowledge base. So that is what these versions of GPT are. So they have tried to, there are different ways to scale up a particular model, scale up and scale out a particular model, right? um, in the case of OpenAI, they have tried to add layers, um, do some alternate attention mechanisms, something called as sparse attention mechanisms. The attention mechanism that we have learned just now is just the basic attention, that is the vanilla attention, right? There are multiple different algorithms for attention, thousands of algorithms for attention, right? So when GPT initially started, it was just using the basic sparse attention mechanism, which is a blend of soft and hard attention. That means it will not only take the local context but also the global context. But since then, there to optimize runtime complexity, because attention mechanism is very it has one square complexity. Now, if you want to, if you're doing it on very large corpuses, right, you want to reduce the complexity or the runtime, and for that there have been numerous implementations of it. So GPT 3, or let's say GPT 2, 3, 3.5, whatever, they are nothing but scaled up variations of your different GPT models, the architecture of which we are going to study today, right, in the code as well later. But this is what it is in a nutshell. Now, if we understand GPT more, so there are different components of GPT. So whenever we say that, whenever OpenAI says that we have this 175 billion model, right, you are going to think like, how do I fit that particular model into a device? Because your laptops will, it is just impossible to do that, right? You might have 16 GB or 32 GB of RAM at max, right? And how do I leverage or build such a big model? Let's say 175 billion. To give you an idea, 175 billion requires something like, for example, approximately 128 GBs of RAM, sharded, across different data centers or different clusters. Okay, so you will have different kind of mechanisms called as splitting the model and splitting the data. Like splitting the model means you are splitting the particular model into different buckets. These buckets are present across devices. These devices can be your GPUs, NVIDIA GPUs, or Intel GPUs, whatever, or it can be like your TPU clusters, like you have from Google, right? You have from TPU clusters. You can shard these models, you can shard these devices across these devices, or you can shard your training data. So these two variants, this is an important concept. That is why I wanted to mention these two concepts are known as model parallelism and data parallelism. And as you will venture into the world of federated deep learning, distributed deep learning of extremely large models, like 1 trillion model, like 175. 175 is a very big model. So you will need many clusters. You will need a huge infrastructure to scale your model. You have to chunk down your model across different shards. You have to chunk down your data into different shards so that everyone will process it asynchronously. There will be a controller or your master, which is your CPU, which will be handling all of your conversions and all of your training from your separate GPUs, right? So the CPU is your bottleneck guy. He's like your traffic police, traffic police in the case of different in your network. So whatever training you are getting from your different GPUs, right, different models, model splits, model sharded GPUs, right, you are going to, that is going to be sent to the CPU. And that is why designing different chips, designing different architectures is very much important for having this kind of very large models to run. So model parallelism and data parallelism, both of these are used in the case of ChatGPT. Now, it was used in the case of GPT-3 because otherwise it would not have fit, in the data centers or in the clusters. The second most important thing is how machine learning, how deep learning in LLM works. We might say that when we build a simple model, right, we have a forward pass and we have a backward pass. The forward pass is nothing but passing through the, just like I told you, it is passing through the encoder layers, decoder layers, and whatever, and you are getting an output. You are validating the output with the corresponding data. If it is not there, you backpropagate that. Backpropagate means take the delta, that is the difference, and you do derivatives across your different layers. Now try to imagine if you are having that big of a model of 175 billion parameters, right? Let's say 128 clusters or 256 clusters, right? How are you going to do derivatives across such a big model? So in the figure that I showed you, right, this is just one block. Imagine if there are 56 blocks of this particular architecture, right? So imagine the number of derivatives. Now, derivatives are being computed at each level. Okay, so at each level, the derivatives are being computed. So imagine the time taken to compute derivatives, right, across from your, let's say, 56 number layer to your zeroth layer, because your delta or your difference during supervised pre-training needs to be accumulated back to your initial layer. So you might think that doing derivatives is quite tough. Think a matrix is doing the derivative. So there is a term in mathematics called as Jacobians. Okay, so and in linear algebra, this is a very important topic, is to understand how Jacobians are used to do derivatives. You do partial derivatives based upon your your y, or your sample. Okay, now, it is very interesting to understand this at a mathematical depth, but that is up to you. Like if you want to understand it, but you have these big tensors. Now, these tensors are not small; they are huge tensors, and these tensors need to do single order derivatives or create Jacobians. Now, that is very complicated, and it will take a lot of time. So in order to do all of that stuff, right, you might have seen that machine learning models take a lot of time. Those are simple models that you develop. Think the scale at which this GPT operates. So in that case, it is very difficult. And there are certain things called as collective operations. Collective operations means that all this kind of matrix computations and all, they will be offloaded to separate GPUs, right? Because GPUs are what? GPUs are, I would say, they are dumb smart people. How? Is because you give a GPU an instruction, and it will continue to do that instruction and will not question you. That is not the case in the case of CPU. CPU has its own ability, it has its own scheduling and everything, right, at OS level. But the GPU also has its own scheduling, but it will disregard that to a certain extent. And whatever your instructions is to the GPU, right, whatever collective call that you provide to the GPU, like any operation that you provide to the GPU, it will execute that. Okay, and it does that very fast. GPU is known to execute the same instruction at a very fast speed. That is why they're used in large language models, large vision models, multimodal models like clip and dal and whatnot. Okay, so this is why GPUs are used. Imagine you are a GPU and you are trying to compute these derivatives. It is very difficult. But imagine also that you are a CPU and you have all these different results coming from different GPUs asynchronously. You need to collect them and store them, and you need to pass them to the previous layer, right? So layer 56 is getting completed, so you have to pass the results to layer 55 in a backward manner. Okay, so the CPU is responsible for that. So CPU processes all the 56 layer computations, processes it, and passes it again to 55 layers, layer number 55. So all this conversion, right, all this send and receive all these different kind of data packets, it's quite time consuming, and that is why your CPU is a bottleneck in many cases. There are different collective calls for that, and you will be going through a little bit of collective calls as to understand how GPT actually scales this kind of huge computations a little bit later. But this is what the GPT architecture is. So think of GPT as like a kind of let's say um, okay, I have it here. Yeah, so GPT-3. So this is how your thing looks like. Okay, so your transformer decoders, you have your transformer decoder layer, which is nothing but the decoder part which I showed you, and see how it is analyzing each and every word. Okay, each and every token has a corresponding weightage, and based upon your input autoregressive tokens weight, it is going to generate certain outputs. It is an autoregressive transformer. Autoregressive means given an input, based upon your input, it will generate an output. BERT is not an autoregressive in that case, because in the case of BERT, you do not generally depend upon what your previous, let's say, token number T-1 or T-2 tokens. It does not depend on it. GPTs or any kind of generative models that you build is dependent on it. Okay. It is uses the same architecture model as GPT-2. Include now these modified initialization is a very complex thing. Two things which I told you about: model parallelism, data parallelism, and something called as collective calls to optimize backward propagation across the large network. So these are kind of modified initialization that they have mentioned. Pre-normalization. Pre-normalization is nothing but sometimes you need to save your normalized weights just to speed up your backwards and your forwards. Okay, that means you just save or cache a certain tensor matrix, right, in your memory, right, in your cache memory, in your not in your DDR RAM, in your GPU cache, right, L1 cache, and you use that for in the next cycle. Okay, uh, so so you have this, and the other important factor is alternating dense and sparse attention layers. Now, dense and sparse attention, think of it like, dense attention is the normal attention where you take each block and each token and compare it with each token. And sparse attention is, let's say you have a chunking window, right, a sliding window, right, but you are omitting certain words from the, let's say, left hand side of your input token. So let's say from the beginning few words you just mask it, okay, and you are just attending that particular token to the right hand side of the remaining tokens in your context window. So that is a particular kind of attention, which is a sparse attention pattern. Now, this is what the architecture of GPT-3 is looking like. Now, you can think of about it like how you might have built or might have known that you have built simple models, which might be, let's say, a few thousand parameters. Okay, think about how 100, let's say a simple 10 billion parameters, this kind of beautiful structure, like a huge structure, how are you going to build? Okay, so you need a huge knowledge base to train that. That knowledge base can be anything. So they have OpenAI GPT has a huge knowledge base on which they're trying to do this kind of training. But now our concern is this part, the chat part, and this is where it gets interesting. Now, I want to look into this particular architecture diagram or workflow, which the people at OpenAI has built or has written. Okay, so ChatGPT using GPT-3, right? But there is certain other factor which makes it so lucrative. It is because RLHF. RLHF means there's a reinforcement learning aspect with human feedback. Now, what is reinforcement learning? Reinforcement learning is that branch of deep learning, not only deep learning but stochastic learning as well, which tries to optimize a particular reward function based upon uh, a collection of your environment and your states and your actions. So think of it like, let's say you are playing a game of FIFA, for example, for by EA Sports, and you have, uh, you know, you are playing against different AI agents, right? When you play by yourself, let's say you are playing against different football players, right? And in FIFA, and they are also intelligent. Where do they know that the ball is present at this particular block, right? Where do they know? How do they know that? Unless we provide the information, right? So that is where the RL is present. RL means that an agent will always try to optimize its rewards, maximize its rewards sometime, in most of the cases, maximize its rewards based upon its given constraints. By constraints, we mean the environment as well as whatever your let's say your actions is going to be. Now, it is a food for thought for you, is that disregard this particular thing on the left hand side for just now. Think of yourself as this particular FIFA player, right? Now, let's say you are playing with Messi or some Ronaldo or someone else, right? And you have a good defender, let's say, for example, Luis, right? Or a good goalkeeper, let's say Neuer or someone. So let's say you are trying to score a goal, but how will you know that you are going to score a goal? Because that particular agent, right, in FIFA is also trying to maximize his own rewards. His reward is when you are not able to score a goal, he gets certain scalar value. By scalar value, I mean, let's say point 0.1 or point 0.2, 2 points or 3 points or something like that. Okay, so uh, that is a very beautiful way. Now, if you think about it, your football, your 3D game is like having three different coordinates or 3 degrees of freedom, x, y, and z. That means your player can move in the x direction, y direction, and the z direction if he wants to take a header, which is the case in the FIFA. Okay. Now, the same degrees of freedom are present in your opposing players as well. So there has to be many things that an opposing player or an agent has to take into consideration. That means based upon your actions. So let's say for simplicity, the action of a particular, let's say your actions is either moving forward or moving backwards or moving on the sideways. Okay, that means kicking the ball forward, backward, or sideways. And in the same way, you have your agent at the your agent, that is your AI agent, right? Reinforcement learning agent, who is the goalkeeper, has the same degrees of locomotion or the same degrees of freedom, right? So based upon how much you distance, how much you cover, right? How much you cover towards the goal, right? It is going to add up to his point tally or reward tally. That is your tally if you are playing as a striker. So let's say if you are, let's say, 2 yards within the goal line or 1 yard within the goal line, right? Or you are in the technical box area, right? So in that case, your points will go up and your agent's points will go down, but your agent has its task to take up its points to its next level, right? So it will try to prevent your goal at any way, at any cost. Okay, so this is how, if you understand FIFA, if you think of FIFA in that way, you will see that there are many complex things which are happening. There is a pathfinding algorithm which is there so that your player can quickly, your opposing player, that is your AI agent, can quickly find the shortest path between you and your ball and just tackle that. Okay, or let's say Ronaldo takes a shot at the goal from outside the technical area, and in that case your goalkeeper will try to activate one of its degrees of motion, that is in the z axis, that is it will jump, sensing the trajectory of your ball, because in most of the cases it will be a parabola, right? Because it will follow a parabolic path. So based upon its calculations, your goalkeeper will try to jump. So think of it like in this way, right? So as an AI agent, which is the goalkeeper, he has so many responsibilities. His actions are three, but how he takes those actions are being influenced by the environment, right? So you have the state action pair and whatnot. Now that is what reinforcement learning is, and there are different aspects of reinforcement learning, like broad divisions. One of the divisions is known as model free RL, and one of the divisions is known as model based RL. Today we are going to talk about model free RL. Now, model free RL means that we are going to understand how reinforcement learning is trying to affect, based upon how an agent is trying to cope up with different factors, right? Changing environments and different other factors. Reinforcement learning has two different broad parts as well. One is known as, depending upon the spaces that they operate in. One is a continuous action space, which is the space you see in most of the events that you play in your video games today, and in certain cases some discrete action spaces as well. Okay, so before we go into that in the reinforcement learning part, now that you know what reinforcement learning is, you might be thinking, right? Um, how does that help in GPT? Now, think of it in this manner. Let's say you are generating certain sequences, the model is generating certain sequences. You take those sequences, and you, as a human, you are the agent. Okay, you are the agent, and you are generating a more beautifully syntactically correct sequence of words or tokens. Now, you feed your input, and the model will feed its input to the reward function. Okay, or the model. The model in this case is known as proximal policy. Just think of it like as a black box reinforcement learning model as of now. So that model will try to optimize its rewards, um, to so that your GPT model can learn how to give out correct sequences in a more syntactically correct manner. All right. So based upon your inputs, which you send to the reinforcement learning black box, which is a deep learning model, right, on continuous action space, that particular GPT network will also try to update its weights. So it is a very complex network that you think. So you have this huge GPT transformer model that is already there, is generating your sequences. You are generating a certain set of sequences, right? Inputs and outputs, and and these two are going to a PPO network or a reinforcement learning network, and then the GPT network is trying to update its weights. And in this way, this is how after thousands of iterations and thousands of training and training aspects, we have this beautiful network called as the chat gpt. Okay, so this is the idea behind what GPT is and what chat gpt, how it was built. Now, um, um, before we move ahead, right, I want to tell something about this reinforcement learning part. So I give you an idea of what reinforcement learning is, but there is certain aspect of reinforcement learning which is known as your, I would say, um, in other words, let's say, how is it important to us, or in the case of, let's say, in any simulation environment, video games or anything, trading and whatnot. So there are certain aspects called as on policy and off policy. On policy means that, so let me tell about off policy first, then you can understand what on policy is. Off policy means that there are two different aspects. One is your value function and one is your policy function. Okay, in reinforcement learning. Now, what is this value function? Value function means, just think of it in this way, as you are an agent, right? You are playing in a field, right? And you want to maximize the number of rewards by scoring the greater number of goals. Okay, so, and the number of goals you score gives you the rewards. So it's a direct, it's a direct, I would say, directly proportional aspect of having this. So directly proportional thing that, the number of goals you scored is going to correlate to your number of rewards that you have. Okay, so in that case, this is called as your value function. Now, in the case of your, let's say, your policy network, right, it is a little bit different. So policy network means that instead of you scoring the goals, you are instructing someone else to score the goals, right? And based upon your ability to score the goals, right? The second player's ability to score the goals, you are going to get the rewards, and you are going to instruct your goal scorer or your striker to change his or her policy. The second one, which I told about, is known as on policy. On policy means that you are acting as a coach, and you are asking your striker, and you are instructing your striker to score your goals based upon certain policies, based upon certain tactics. In the case of your value based, you are itself the striker. So that is the difference between the two. Okay. And in the case of PPO, it is known as an on policy method. On policy means that there are two networks. One is known as the agent and or an actor, and the other one is known as the critic, or in your case, it can be the coach. So let's say your coach is Pepe Guardiola, and you're playing for, let's say, your Benzema or someone. So your coach is telling you that your striker should attack from the left wing, right? So in that case, your actor is your Benzema, and your coach is your Pepe. So this is how the actor-critic networks, the idea behind actor-critic networks, evolved. So you might think that if we have this kind of beautiful network, so there might be some kind of competition between them. Of course, there is. So there is always a competition between them, between the actors and the critics, so that the critic will always try to maximize its instruct the player. There is associativeness. In the win of the player or the win of the actor, there is a win of the critic itself. But what it will do, there are different kinds of different segments. There is competitive actor critic networks, there is associative actor critic networks. So if we consider the associative actor critic networks, what will happen? Based upon the actor's actions and the rewards attained by him, the critic will update its policy and then pass on its policy to the actor. Like, think of it in this way: like Benzema scores from the right, could not score from the right hand side. So that is a negative penalty for Benzema, and the critic, which is your coach, is taking his responsibility. He's understanding that he should attack from the left hand side. So he instructs, he passes on this weights to the to the striker, that in the next case he should pass from the left hand side. Okay, so this is how your associative actor critic networks work. PPO is a variation of associative actor critic networks, where your critic is trying to make the actor a better version. All right, and this is one of the major parts of the critic. The second important thing is advantage functions. Advantage function means that in the case of machine learning, right? Machine learning means, or in the case of any kind of supervised deep learning, you will always see people use the term minimize the loss function, minimize this, minimize that. This minimization principle, it has come from certain place. Why? Because in the case of any kind of deep learning applications, you are bound to have something called as a minima, or a loss curve. This loss curve is based upon how many dimensions you operate in. So it can be multi-dimension depending upon the input size, or your input dimensions in your particular corpus, right? In your input to your machine learning model. And your task is to optimize the model by reducing the errors that I talked about. Okay, so that is why you need a minimization function. But in the case of reinforcement learning, that is not always the case. Why? You can also think about it. Why? Because, as I have told you, that there is a reward function, and the task of your actor or your critic, right, is to maximize that reward function, get maximal rewards as possible. So if you just apply a minimization policy on your reward function, it will not give you any good results, right? So you need a maximization policy on your reward functions. So advantage functions are nothing but your how your agent, or how your critic instructs your agent to maximize his number of outputs or rewards. That is why you need an advantage function, and for that you need global ascent, not global descent. Okay, in the case of standard supervised machine learning, you will see global descent and whatnot. But in this case of in this case of reinforcement learning, along with global descent, you need to have global ascent. Why? Because let's say the player made an error, the striker made an error, right? The actor made an error. So you need to reduce that error. So for that, you need to train your model with the global descent. That means minimizing your loss. But also there is another function called as a reward function, and you need to maximize that. So that is known as your maximizing your reward function. So that particular reward loss needs to be maximized. So in the case of reinforcement learning, right, on policy reinforcement learning, you have two things which are contrasting to each other taking part. One is your minimization and one is your maximization. So this is the beautiful way how reinforcement learning is completely different from your any kind of supervised training approaches that you find, in a nutshell, right? Without going into the mathematical nitty-gritties, there are certain mathematical proofs which are there. If you are inclined, and if you know about certain if you're well versed in linear algebra, calculus and all, you can definitely take a look. Okay, so and now if we go back to what on policy, we have understood that what is actor critic, we have understood that what is on policy and off policy, and we have understood what is model free and model based RL, model free RL, right? So in our condition, we are going to take a entire cluster of those. So PPO is an actor critic model, PPO is an on policy model, PPO is based on continuous or discrete action spaces, and it is a model free RL. Okay, so that is the beauty of it. Okay, so PPO, actor to critic, is an on policy method, and it can in order to reduce the errors or the error margins, right? You have a certain thing called as a KL divergence term. Okay, KL divergence term is used when you have two different loss curves, right? Two different statistical distributions, right? And you want to minimize the effect of distribution, difference of distribution between the two loss curves, uh, or the statistical distributions. So KL divergence is used to measure the degree of difference between two different statistical distributions, and it is used widely in most of the deep learning, or let's say as a KL divergence loss or something like that. Okay, PPO has different approaches. One is known as the penalty loss, and one is the clip loss. We are not going to focus much on those. Those are just different variations of writing the loss functions. If you are interested, I have certain repositories which I have linked below to if you want to understand how PPO works in detail and how it can be used in other aspects as well, like in trading or other aspects. I have a separate repository for that, so you can understand it better in that case. So if we go below, then we have the Chat GPT, right? So some important facts about ChatGPT is the infusion of PPO, that is proximal policy, is semi-supervised, which means that your agent will try to your the agent, let's say in your case you are the agent itself, as it is human supervised, and your PPO will try to understand that and understand it better and try to give those particular weights back to your GPT network, so that it can replicate and produce more syntactically correct output sequences in the next training step. Okay, this implies that a reward function is moderated by human supervision on the previous results. The initial LLM generative sequences are ranked based upon the cumulative rewards based on human supervised PPO. So there is a ranking mechanism which is taking place, right? So this ranking of the different outputs is done not only by the human supervision but also from the output of the model, PPO model that you are trying to generate. Okay, and the next thing is that the Chat GPT, both models are given a prompt, and you are trying to get an output response from it. So the tuned LLM responses are scored with the reward function, which is then used to update the parameters of the fine-tuned LLM. Now, if you see this complex part, the initial language model part has this particular base text, which is trying to generate its Y output. And the tuned language policy, or the RL policy, which is the PPO network policy, it is trying to generate something with the human, RL HF feedback, right? So in this case, the reinforcement learning is trying to update its policy and is trying to feedback this particular network, right, to the initial language model. And you see the scale divergence policy which is being applied in this case. The scale divergence policy takes the PPO output of your YX and compares it with the base model that you have, the base initial language model that you had started with. So this is how it comprises them and it merges them together, so that, and it updates the initial language model so that it can produce better sequences in the next iteration. So this is the way how ChatGPT operates in a nutshell, by using PPO, by using GPT-3 architecture, and it produces the different sequences. All right, and just the final thing which I want to say about ChatGPT is that, since the reason why scale divergence is used is because we do not want to deviate from the results, right? We do not want to deviate from your human supervised output, right? Because otherwise the optimization might be very bad. It might not give you a good result. So in that case, in order to prevent gibberish output, we are maximizing the reward to the model score. Now, a labeler is also present, which demonstrates the desired output. The labeler in this case is your human supervisor, and OpenAI had thousands of these, trainers available for us. So this to fine tune the results of your output model and your results. Okay. In this case, this data which is used to fine tune GPT-3 is the same data that is being used, and this knowledge base is constantly getting updated. So this is how your entire output is getting is being run in this case. So just I want to stop sharing for certain time, and I want to focus on, if you have any theoretical questions on this aspect, right? I have a lot of questions which I can see, so I'm going to answer a few questions of that, right? So what is positional encoding? So the first question, we can see that there is a positional encoding question, right? So beautiful question. Positional encoding means that whenever you use a tokenizer, right? Because your machine learning or your deep learning model cannot understand how you are trying to, because your machine learning models always try to see tensors. Tensors means numbers and floats, right? Floats. But how are you going to convert your tokens into floats? You need to have certain tokenization policies. Now this beautiful tokenization policy of or positional embedding means that depending upon your position where the particular token is, it will try to assign its tokenization value, like that. So there are different kinds of positional tokenizers. So for example, you have byte pair encoding, where you take a particular word, you chunk it down into smaller words. So let's say walking, walk plus ing, so they will be separated into separate sub tokens, right? Then there is, subword level tokenization. Then there is, most commonly in GPT we use BPE, byte level tokenizers, where you further break down a particular word, let's say walk, into WA and LK, as those these bytes are limited by the number of your tokenization byte limit. So it can be, let's say, 4 bytes or 5 bytes. So based upon that byte, it will truncate and split into smaller subwords and sub tokens. So it is a very beautiful thing. And a positional encoding means that you are encoding those particular tokenizers based upon their relative position in the particular corpus or in the particular context window. That is how your positional encoding is. And why do we need that information? Because unless you give a positional encoding properly, right, you cannot get a proper output. Your language model will not understand which token comes after which token, although there is attention mechanism present, right? But it is not that much powerful to understand which token comes after which token. So that is why you need your positional encoding. The Google research people, when they first wrote this transformer paper, they started with hypothetical positional encoding by using sinusoidal mechanisms, sinusoidal functions. And later, this was a hypothetical one which they found to give good results. But I would say that that is not the entire, there are different functions which have been coming from since then. But yeah, so that is the first question. And yeah, no more questions as of now. So I want to take 1 minute off, right? 1 minute off, so that you guys can digest this entire thing before we dive into the code, right? Because the code is going to be a little bit complex. For those who are not aware of Python, I would recommend you to start building, if you're interested in deep learning and these kinds of applications, right? Start trying to build different different small models, like let's say resonant 50. Start with resonant 50 resonant models, vision models. Start with different approaches. Understand mathematical implications, because writing models is very simple, right? Smaller models, you will find it everywhere, but understanding is what is required, right? So do you think ChatGPT threatens Google? So search engines are completely different. ChatGPT is like something else altogether. Okay. Search engines employ not only language models, there are different things which are happening in search engines. You have multimodal models, right? You have ranking algorithms. So in order to build a fine-tuned search engine, you need to have proper ranking algorithms. Okay. These rankings are nothing but how you, let's say, when you type a particular search query, how your results are going to come up on the screen. This ranking is a factor of your multimodal model outputs. Multimodal model means you take your inputs, vision inputs, audio inputs, text inputs, and whatnot. When you type in a Google search, you get text, news, or image, audio, video, and whatnot. You get different kinds. These are all multimodal outputs given upon your input text. Okay, so you have to rank your multimodal outputs based upon your different outputs. Now, ChatGPT is just like a huge language model, very large language model trained on very big corpuses, very big corpuses on thousands of clusters and a huge infrastructure, right? But there is certain catch behind it. It does not have intelligence. Intelligence means that it is throwing out, or it is barfing out whatever it has learned. It does not have intelligence on its own. By intelligence, I mean, let's say there is a concept in reinforcement learning, which is known as where the agent itself learns. Agent itself tries to think rather than agent choosing a certain policy. So this is known as, I'm forgetting that particular term, learning to learn. That there is a famous paper in reinforcement learning called as learning to learn, which is known as meta learning. Meta learning means that instead of the agent trying to learn, right, the agent will try to understand the environment better. Instead of trying to just optimize a loss function, as the critic has told, it will not try to do that. It will try to optimize the environment itself. It will try to optimize its own state action pairs itself. That is what meta learning is. Meta learning is understanding and training the metadata which is present in its memory. So the agent will develop general intelligence, which is known as AGI, artificial general intelligence. ChatGPT does not have AGI. Chat GPT is like a guy, let's say an infant who has now become big, right? Has fed in with thousands of knowledge bases and thousands of corpuses. Okay, so Google is completely separate. Chat GPT is completely separate. Chat GPT can be used in certain search engines just to just to increase that particular output of a particular knowledge based query, but it will not replace anything. So and speaking from a subkernel level, right? Like from what I know about these large language models and all, inferencing is a challenge, is a huge challenge. Like let's say you have 175 billion parameter and you want search query results in 0.003 milliseconds, right? How will you do that? Google does that. How will you do that? So you let's say you employ any kind of caching mechanism on your hardware and on your software, right? But still you will not be able to beat that particular score, that this much seconds required to take your get your results and your output expressions. Okay, so you have to understand this, and that is, I hope this answers your question. Chat GPT will not in any way, it is a good addition, but it will never replace any search engine that is present in the market. Okay, unless Microsoft is trying to build that in its edge build and whatnot. So I personally, I look into the LLM models aspects of Microsoft, for because we develop kernels for it, right? So this spans any kind of GPT that you are seeing, Neo X, Neo, and GPT and everything, right? So GPT 1, 2, 3, and everything. So, and I can say that it will not be looking into that in the near future. So I hope that answers your question. Yeah. Okay, so let's start with the code part. Okay. Uh, so the reason I was taking a break is because I wanted you to digest what I have told in this span of one hour. Because trust me, it is what I have just told you just now is like last 10 to 12 years of, more than that, 10 to 12 years of at least machine learning, particularly deep learning and federated deep learning workflows, right? What the machine learning area has covered. And reinforcement learning is a very, very tough topic. Trust me when I say this, it is a very tough topic. One of the toughest fields in deep learning is RL. So, and it requires a very good level of mathematical understanding to understand and try to replicate that. Transformers and all, they're pretty much straightforward. It is not that much complicated. It might seem complicated to you because you're starting afresh. Now, I know that for a fact that there are people who are not fully aware of Python, who might not be well versed with coding languages. So for them, it is of course, I will say honestly that this will be a challenge, right? So to understand this, and for them, I can just explain them in a pseudocode manner so that they can understand the logic flow, and later when they are well versed with the whatever languages they're trying to build, so they can try to build their own as well. Okay, so there are, if you go into this Chat GPT API, which I've also linked. This is the API which I was testing yesterday, right? So you can see, right, what is, I have questioned this, that what is your architecture, what is the architecture of your model, and see the output that they have, that this particular OpenAI chatbot has given. This is the official chatbot API. So I am a large language model trained by OpenAI, and my architecture is based on a transformer neural network. Was introduced in 2007 paper by Vaswani, which is the Attention is All You Need paper, right? My architecture is also based on a Hadoop neural network, right? It's massive amounts of data and fine-tuned. Now let's say, how when is your knowledge base cutoff? I think I have to reconnect that, maybe because it has not. So just in case, I have just asked some questions so that about the model itself. What is your sequence length? 2048 tokens. Now, what do we mean by sequence length? Sequence length means, think of it as, in other words, as the size of your sliding window, like 2000 to 2048. So 2049 to, let's say, 4096, right? Something like that. Okay, so it will go in that range. Okay, the sequence length is an important hyperparameter for language models, and you can just query and ask different questions about the model itself in this particular area. So it uses model parallelism, which we talked about. And let's see if we have any other questions. Whatever questions you want to ask, you can just go and ask about the model itself. Like, what I wanted to ask was knowledge cutoff. What is your knowledge cutoff? Let me see. 2021-09 September. That means I'm aware of the events and the information up to September 21, right? Any events or information that have occurred after that date, I may not be aware of. Uh, so let's say what happened after 2021. So let's say, uh, 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 let's say, okay. So that is good. So that is good. So I just wanted to test that whether it is actually telling the correct thing or not. So it is apparently it is telling the correct thing. So let's ask another question. Who is the what happened after 2021? Uh, any big thing happened after 2021? Yeah. Let's say this one. This is another big thing which happened in the tech world. React say. Uh, okay, so I think this is correct. This is not. I think that's fine. So I saw a post somewhere that someone had tested some information from 2022, and this model had actually picked up that information. So that means it's someone. So there is an option for setting this particular right or wrong, right? And if you specify this, you give an option to ideal answer. Now what this will do, this will just add, this is your supervision. That means you become an agent, and you or in other words, in the PPO policy, you are the critic or the coach, and you are sending that this is my ideal answer, and you are sending it to the PPO policy. And what OpenAI will do, it will take this output, and whatever you have provided, it will feed into the model. It will again retrain it, right? And it will send and it will update its model weights for this particular question, particular set of input question tokens. So this is how your chat GPT is working at the back. Okay. So there are different implementations of it, right? You can use this quick start tutorial, and there are certain I would say open APIs available for this particular use case. Now there have been certain repositories which I was looking up on ChatGPT. This particular person has done a very good repository for accessing the API. But one important thing is that your because since they have not open sourced the model yet, they have not open sourced the model implementation yet, so it is still a haywire, right? Everyone is using the API, everyone is designing certain apps with their API, which is quite simple to do. It is not quite a difficult challenge. You have REST APIs, and you just query them, right, using a token and your session token and all. But what will happen if you want to build something like this, like a smaller version of it? Now I was trying to build this, right, since it is a very complex model, right? So, and there is no resources available anywhere. I was trying to build this, right? It is not complete yet, it will take some time. So but the architectures are present. So the architecture, by architecture I mean that a GPT architecture and a PPO architecture, so that you can understand how we write the code in the case of this particular block. Now in this case, I'm going to talk about the attention mechanism that is present in GPTs, or in the case of your transformers in general. Now if you remember that there are I had talked about three different tensors which are present while computing the attention mechanism. One is your query, one is your key, and one is your value. So these three tokens, these three input matrices are being multiplied together and done some different kind of combinations, right? Based upon your input positional encodings, as well as your token ordering of your tokens in a particular sliding window, right? So in this case, you have your three different matrices, right? So which is nothing but your, let's say you can initialize them using simple dense layers, or in the case of TensorFlow or PyTorch, right? And there are certain some important calculations which are being done. The query and the key are multiplied together, right? And then they are scaled by a value, let's say any value. The default value is 8, but it can be scaled up to any value, right? And then you wrap that output in a softmax activation, which I talked about. Now, why do we need these softmax activations and q and k? It is because for each token we are trying to find out uh, uh, what is that particular word, the correlation between your particular token to your input corpus, or in your sliding window, right? This correlation mapping is done by using your query and the key and these value matrices. Okay, for each token tensor you have this query value, query tensor, you have this key tensor, you multiply them, right? And then you softmax them. Why you softmax them? Because as I have told you, softmax is for a categorical distribution. And when you have a categorical beautiful distribution available, right, then you can use that particular distribution to say that yes, this particular token attends to this particular sequence, or let's say sliding window, right? And has a very high correlation with this particular sliding window. In that particular context, this word is present with a very high importance. Okay, so this is how your attention mechanism is being done. uh, these terms are nothing but the lingo of torch, right? And in other words, this is the architecture that we have seen. Okay, now if this attention mechanism, you are going to have this layer norm. Layer norm is nothing but a normalization which is being applied. Normalization means based upon your moving averages, right? Based upon your standard deviation and your mean of your any kind of distribution, right? You norm that particular matrix, you norm that particular input tensor, right? So layer norm is a way of normalizing your layers, your input components of your layers, which is nothing but your tensors, right? And then you are going to have FFNs like feed forward networks, which you saw in the transformer layer, nothing but this one, this linear layers, in and linear. Okay, and this GALU is an activation, fancy activation, nonlinear activation, which is a mathematical function which is written over here, right? So it is a nonlinear activation used to give a very good output. Okay, and this is your transformer block. So this particular small block is your one decoder block, right? This is how you write a decoder block. Pretty simple, right? Because in this case you are going to have your decoder blocks and you are going to stack them up one on each other. So you are just going to use a for loop to stack them. That's it, you are just going to use a for loop to stack them. Now in this case you have this your n layer, n head, vocabulary size and whatnot. And you are going to have this different, see, you are based upon this different architectures that you see, you are going to have different kind of layers. You are going to have layers for your heads, you are going to have your embedding size, you are going to have GPT-2 XL, which is 48 layers. Think of it like the image which I showed you is just one layer. And now if you just run a for loop to have 48 different layers, how big that particular model is going to be. So this is how you build a default GPT to GPT, any kind of GPT variation transformers, right? Now, in this case of leveraging, yeah, and the rest part of the code is just boilerplate code, right? This was the main crux of it, which I wanted to highlight. This block, this attention mechanism, right? This causal attention mechanism, and this GPT network, how they are merged into the GPT network. So all, okay. So this is just a way of writing Python code. You can just look into the code in more depth. So that also this has been adapted from Karpathy's code, right? Min GPT code to support DDPs. DDP means I had talked about model parallelism and data parallelism. Now, model and data parallelism ensure that when you are building, let's say, a 120 layer decoder transformer, your model does not flow out of your GPU stacks, or it does not go out of your GPU stacks, or it does not give OM errors, and it gives a proper good latency, right? Good latency in terms of your training and your periodic training, which is a factor of distributed training. Okay, so for that we have this distributed training lingo, which is known as rank and world size. Now, in a nutshell, think of it like how many devices you have. So let's say I have 4 GPU devices, right? NVIDIA GPUs. So your world size is going to be 4. and your ranks is going to be from 0 to 3. Okay, so what it will do from your CPU, each of your CPU will offload, let's say, part of your model. Let's say 48 layers, 48 divided by 4 will be 12 layers. So 12 layers will be offloaded if you're doing model parallel to GPU 0, GPU 1, GPU 2, GPU 3, right? 12, 12, 12, and 12 each. And then while taking back the data from your GPU, like allocating the data and taking it back from to your CPU, you are going to get a synchronized overflow of it, right? So this is how distributed parallelism works for model parallel. And if you have data parallel, you are going to shard your data. Let's say you have data of, let's say, for example, 100 size, 100 sequences, right? You're just going to shard it into 4 blocks, 4 GPUs, 25 each, and same way this will happen. But in this case, the entire model, that is a 48 layer model, will go into each of them. That is, model will not get sharded, but data is getting sharded. In this case, if you want to shard your model, then, like I told you, your model will be split into separate blocks, provided they are properly divisible by the number of layers and attention blocks mathematically to make it possible, and then they are going to offload the training. Okay, so this is just one important aspect of it, because without that, no large model, no LLMs that you see currently will get trained. Okay, optimization is one part, functional thing is one part. So whenever you are trying to generate the sequences, you are just going to pass the input tokens through the sequence of decoder stacks, right? Through the tokens of decoder stacks, and it is going to generate, and the final output is going to be the softmax, which I talked about in the image of transformers. So the and after that, whatever softmax scores you get, based upon the previous set of input tokens, right? It is going to rank them based upon the softmax scores. And you are going to select the top K. That means top K means the either it can be top 2, top 3, if you want to generate two tokens at a time, or if you want to generate 3 tokens at a time, 4 tokens at a time. There is a utility function in Torch to generate Torch, n tokens, depending upon your n set of input tokens, right? So that is how you are trying to generate your output based upon your inputs, right? For those who are not fully aware of Python, I would recommend you to just understand the pseudocode, how it is happening. So just like I told you, the attention is a mathematical tool, and we are stacking different layers of attention and layer norm and feed-forward networks on top of each other, like we have a decoder network. And the output, we are passing the input tokens to the output and to the softmax layer, and we are selecting the top 2 or the top 3 of that. Okay, and in order to make it run on different GPU devices in a distributed manner, we are going to shard off different parts of the model in different parts of the code, right? Now let's move into in the request of time, because I want to keep a few minutes for the question answers, right? I want to give you an idea about this PPO policy, which is very difficult to understand now, and and for this, I want to just keep it short so that you can understand it later as well at your spare time, right? Go through certain blogs. I have linked many resources in this particular blog. Go through OpenAI's blog, Jim blog, because that is the starting point of your reinforcement learning journey. That should be your default starting point. Okay, that is a beautiful blog where you have different concepts, right, available to understand how Jim has different environments, simulation environments, where you can employ different algorithms, and you will understand how each of them interact if you're interested in this. So we are going to have an actor network and a critic network, right? So this actor network and the critic network are more or less the same architecture they have, but what is the difference between them is how they create the loss function, right? So your agent is going to so your, let's say this is a simple actor network, right? And this is your critic network, right? This is a simple PyTorch critic network. You can have a simple dense layer of critic network as well. So you are going to address, your agent is going to have this actor and the critic, and it is going to have a PPO memory. One important thing which I forgot to mention about off policy and on policy, kind of the major difference between off policy and on policy is that off policy has a kind of a buffer memory available, because since in off policy there is only a striker, there is only a player, there is no coach, there is no critic, there is nothing, there is only one actor, there is only one player. So he has to remember the values he has got, the number of goals he has scored, for example, in his memory, in his buffer memory, in order to fully replicate that and do that again. But in the case of on policy methods, right, in the case of on policy, that is not required because there is always a coach present, and the coach has account of whatever his previous calculations have been, whatever the goal scoring and whatnot is there. So since in on policy network there is a critic network available, right? We do not need this PPO. We do not need this buffer memory. But in the case if you want to build a proper PPO network, if you want to add certain, let's say, robustness to a PPO network, you might be using a buffer memory. You can use a buffer memory so that the coach can recollect. The coach can also think, the coach can also think that, on this particular season, this guy has scored, Ronaldo has scored this particular goal from the center, right? So he can think and he can say this, right? So it is just flexibility that you have, and based upon this there are different flavors. Just like I told you, you can plug and play different components to give you different architectural purposes, right? So let's say you have PPO and you have two different critics. You can have two different critics. You can have one different actor. That means two competing coaches and one player, right? And the player will select whichever coach gives the best policies to score the goal. So these kinds of architectures are also possible. Uh, A3C PPO, actor 3 critics, right? A4C, distributed actor critics. So different kind of plug and play models are available because these are all different plugs and plays, right? So you plug a model and you just get the rewards from that. So it's a very complex thing, right? But in lucid terms, you can plug and play different aspects of it. Just like in the case of GPT, we have, you can plug in different components as well. And information on this, just FYI, is that you might have heard about other models, which is known as, T5, for example, or BART, BART, or mainly I think you might have heard about T5. Now these models are both encoder decoder dual kind of models. So that means these layers not only have the encoder from BERT, but they also have the decoder from GPT. That means this kind of language models are capable of doing both the things. That means question answering, that is discriminatory set of tasks which BERT is able to do, question answering, causal LM, let's say your NER and whatnot. Plus, it can do generative abilities, which your GPT has. So these kind of large language models are called as dual transformers, okay, like T5 and whatnot. Then you have this separate set of transformers called as multimodal transformers, where you have your separate LLMs, let's say a GPT network, and you have a vision transformer. That means a transformer model built for vision, like computer vision. Let's say a ResNet transformer, something like that. So you can merge these two outputs to give you multimodal things, which is what is happening in the case of Clip, another popular model from OpenAI. So this particular model, where is ChatGPT? Go to this OpenAI research and you will see all this multimodal neurons in artificial networks. So this is where what I talked about. You have your vision transformer, you have your GPT language model transformer, fuse them together, and you have your multimodal neurons, right? DALI is the same thing. Clip is another same thing, right? So just go through them and read through them. That is very difficult, beautiful to understand. Yeah, as I was showing, where did I go? Where did I go? Yes, I think so. Yeah. So in the agent, you have this actor and the critic network as well as the policy. Now, for each training step, what it will do, your critic will sample your inputs from your sorry, the input to the critic will be the output of your actor, because based upon the actor's goals or actor's actions, the critic will take its next policy. It will change its policy, right? So in that case, you will have your critic to take the output sequences from your actor and then feed it into that your input model of your critic, okay? And there are different there's a clip loss which is present in this case. And I want to show you another repo which I have, right? Which is another PyTorch implementation which I have done for another seminar, right? On deep reinforcement learning. Yeah, for trading purposes, right? So this is for here you have different a broader section of the approaches, TRPO, A2C. You might have hard DQNs. So let's stick with TRPO only, which is another variation of PPO only. So here you can see that the loss, okay. There are different kinds of loss functions. You might have seen about the KL divergence term which I have talked about. Scale divergence of two distributions P and Q is nothing but minus P log P by Q, minus P log P by Q of two statistical distributions. That is the simplest mathematical formulation. Okay. So in this case, we are sampling the output of your actor and your critic, right? Or from your actor at two different time steps as two different statistical distributions, and we are trying to take a Kehl divergence of it. So this is how you design your loss function. This is your TRPO PPO penalty loss, which is nothing but a fancy way of saying PPO loss. Okay. The reason, because TRPO is a separate algorithm on which PPO was built, trust region policy optimization. Okay. So I'm not going to go into the details of that, but you can take a look in your spare time, and also you have your different approaches of your uh, you know uh, let's say OpenAI gym, right? So you are going to feed in your input corpuses, right, from your GPT-2, whatever forward you are generating, right, generating the tokens using top k torch.topk, which we talked about, and we are going to feed it into this particular block of code, which is your input samples, right? And then you are going to this total loss dot backward and zero grad, this implies that you are going to generate certain outputs, and these outputs will be coming out in the form of probabilities, floats, because we are going to take a softmax distribution from your actor, right? Because in this case the actor does not have two outputs, it can have many outputs, right? So in this case we are going to have another softmax distribution. This is nothing but a softmax distribution itself, right? In crude words, softmax distribution from the actor, so that he can properly score the generate the sequences in our case, because our use case is generating proper sequences, and we have to feed that again to the GPT model. So that linking is still left in this particular repo, which I will update. I have not updated it yet, but this is how your architecture entirely looks like. So you are going to have two different blocks. One is your GPT network, and one is your PPO network, right? And you are going to fuse your network on this. Now, just as an FYI, since they have not open sourced the code, and there is no source of code available for ChatGPT anywhere on the internet, right? So this is my implementation and my understanding of the paper, what they have written, and still it is not complete. I have to write some, it is still pending, but this is what it looks like in a nutshell. Once you get the logic, you can just yourself, you can try, if you are well versed in Python, you can yourself try to write the code in any frameworks. At it, frameworks is secondary. Torch, TensorFlow, Sonnet, anything, right? That is secondary. Lightning and whatnot. So that is secondary. So this is what I wanted to talk about. And let me again share my screen. I forgot to just yeah, just let me share my screen. I just stopped sharing it. I hope you can see the screen. If we just move back, so this is an example which we were talking about, which I showed you, right? And some resources for OpenAI blogs, right? If you want to have some resources available for
Sir,
hard.
sorry to interrupt you. The screen is not visible.
Screen is not visible. Okay.
Yeah.
Okay. Thank you for informing. Let me see. Just 1 second. Okay. Let me see. Let it load up. I think so. It is. If you can see the screen, just let me know. Right. I hope you can see the screen. I'm hoping you can see the screen. Um, yeah, I think it is visible, right? So if it is visible, then these are certain blogs which you can look into. This is the Instruct GPT paper, which is actually the main point of instructing the first point of Chat GPT. This is the paper which you can look into. This paper was on Twitter somewhere, and I picked up the link. That is why you see this t.co. It will point to your arXiv link, right? And the second thing is that these are my concluding statements. If you want to connect, uh, I do a lot of things on my GitHub. I'm more active on GitHub than on other sites. So in that case, I have some few ideas in mind, right? Like creating certain separate backends, certain separate frameworks altogether, like we have for PyTorch and TensorFlow, right? So for distributed training and all. So that's all about me in a nutshell, and about the session in a nutshell. And I hope you guys understood some part of it. Like if you understand 20% of it, it's more than enough at this stage. Because nowadays, everything is on the internet. You can learn about everything, and that's all that I wanted to talk about. So if you have any questions, and Just let me know. It is a lot of things, but yeah.
So, thank you so much, sir. That was a very insightful session into the world of ChatGPT and AI. I mean, there's so much to learn today. So let's start with the Q&A then. Um, yeah, there's one question from Anand. So he says he's working for 3 lakh from the last 2 years and not happy. Could any changes? So I guess how if someone is looking to change their domains from something to AI and, and ML, or someone is looking to start their stream in AI ML, so what would you suggest on how to go about it as a career?
So the first thing is before MLAI, right? MLAI are two different. First of all, people say MLAI as if they are the same thing. ML is different than AI. But I would say the first thing is getting the basics straight. There is nothing better than writing code, right? Like writing good code. Your fundamentals in any language that you write should be very much clear. I will tell you, this chat gpt, the way how you are building this chat gpt, this attention mechanism, right? If you want to reduce the complexity, right, there are certain if you go into because we are running this model based on certain platforms. I will give an example. On certain platforms, either PyTorch or TensorFlow, if you go into the TensorFlow source code and you understand how this attention mechanism or any mechanism is going into the backend of TensorFlow C++, you will find that there is DFS algorithms. There are flood fill algorithms which are present. So this is what I'm trying to say is that your basics on data structure should be good. Not a competitive coder. I'm not a competitive coder myself, but you should be well versed in writing code in any language. Let's say any kind of algorithms. Popular algorithms should be well known. I mean, that is the starting point, and once you write that in any language, you can obviously replicate. Writing code for deep learning models, right? Unless you are writing from scratch, which I do, right? You are generally going to use certain wrappers. There are so many different. TensorFlow has wrappers. Keras is there. You have PyTorch Lightning is there. You have PyTorch is there. Different things are there, right? So many things are there. So it is very easy to write a simple piece of code, but when you understand the internal parts, right, tricky parts, like how, let's say in the TensorFlow you have something called as gradient tapes. In a gradient tape scope, how you are going to select and abstract gradients from your 2 layers out of your 5 layer model, and just do certain internal computations, play around with it, and again feed into the next 3 layers. So this part of the code level understanding is essential and is required. And trust me, in the case of your interviews, very few from my experience, I have taken and given. I have been on both sides of them. It is very people will not ask you all this type of stuff, but it is very, once you know the thorough picture of your backend of your framework or your model or your everything, it has just become a cakewalk. And in many cases, your interviewer will also not be knowing that much things as what you might be knowing. This is a very practical example which I'm telling you. So it is very good to have a, but you need to time. You need, of course, it takes time. It takes time. Everything takes time.
Okay, so would you do you recommend that as a beginner I start making models myself, or should I use libraries and import the ready-made models to
I
train
always
the data?
recommend, if you have time. I always recommend, if you have time and if you are well versed in any code, your first challenge will be to write in. Let's write a simple perceptron layer in like a feed-forward dense layer in C++ or C, or in scripting language. Try to write that. Or if that is too difficult for you, try to write that in NumPy. Okay, only NumPy. No other stuff. Trust me, you will learn so much that about you will learn many things. I have done the same thing. I have built for LSTM transformers, everything in C++, right? So you might have understood so how this internal layers they merge, right? In NumPy as well. So I have the NumPy code in my GitHub somewhere. I had wrote it way back 2 3 years back for LSTMs and all. So this is very interesting, and you will gain a lot of knowledge. And of course, if you have the time in college, I know that you have the time, so try to experiment with it, and also try to participate in OSS, open sources, right? If you're interested in ML stuff, if you're interested in deep learning stuff, try to contribute to TensorFlow platform. if you're trying to contribute to hit me up, so I can patch you through the TensorFlow folks. Okay, so TensorFlow platform is there. You have PyTorch. If you're interested in PyTorch, you can work in PyTorch platform. So this will actually make you understand frameworks at a lot more level, because these are not simple frameworks. I tell you, there are millions of algorithms which are running at the back end. Algorithms to how you can scale up, how you can shard your data, how you can offload your attention to one particular GPU. Thousands of algorithms are there. I cannot name all of them. So yeah, and how these graph mechanisms are happening internally. There is graph. All deep learning frameworks employ graphs at the back. Any block you write a piece of code, dense layer, that is a node in the graph. Connecting those nodes to get an output. That is how these frameworks work. Uh,
Okay.
so that
Uh,
is how I would say.
hmm. Going on to the next question by Kashish. In what ways can you differentiate between ChatGPT and Google's Lambda?
So the person who is asking this, what is the main feature of Lambda? I mean, uh, so Google and OpenAI, not only Google and OpenAI, I mean, DeepMind and OpenAI are always in a fight between them. They are always fighting, like for who can build better models and whatnot. Lambda is somewhat similar to this what we have for ChatGPT. It is also a generative model, but it is a simple dual transformer. It is not a simple decoder transformer, right? So Lambda is uh, the major difference between them is you can use Lambda for any kind of tasks, right? Any kind of tasks. So generative is also good, but it is competing with ChatGPT from how I know. But I don't want to go into the nitty gritties, because Google's Lambda has some aspects of it which is hard binding to CUDA binaries. So you are going to have, let's say, some optimizers, Lambda optimizers, right?
Hmm.
For They do not use fused atom or something like that. They use different optimizers for their in the forward pass, right? Forward or backward pass, whatever you want to say them. The optimizer layer is different. So I think they are separate. They are competing with each other, and when there is always a healthy competition, you can use either of them. We are getting the benefit of it. So Google's Lambda is also, I think Google's most of the source code is open sourced. I think so you can
Hmm.
readily access them. So
And if I'm not wrong, they are based on the same transformer
so the architecture, what Vaswani has
architecture.
given in 2017, that is being used everywhere.
Okay.
Okay.
So next question by Akanksha. What is the difference between AI, ML, and deep learning? This is a
So
very
very broad question.
important question. Yeah.
ML means machine learning, deep learning. It is a Venn diagram. AI is the broader Venn diagram. Inside that you have machine learning, and inside that you have deep learning. That is how I can say it. So AI is something called as artificial intelligence. In other words, what I had talked about AGI, right, in my seminar. So it is AGI, artificial general intelligence, which only up till now only one sector of deep learning is trying to use that, which is reinforcement learning, right? It is trying to do something called as meta learning, learning from the environment itself, learning from outside, not trusting on any policy or not trusting myself. I'm learning from outside, right? So that develops general intelligence. um, what is his name? Forgetting his name. The Lekun Yanli. So he is working on that AGI for at New NYU, right? He himself has told that ChatGPT, these language models, they become boring to a certain extent, because you are feeding something with huge corpuses, and they are training on large data sets on huge models, and they are barfing it out. So this is effectively that. But that is why why ChatGPT is now so good is because now you have this reinforcement learning factor, which is trying to imbibe a certain aspect of your AGI, general intelligence, into your LLMs, right? So yeah, that is how I would say it. AI is a broader field. Is the broader field. Deep learning is just a small section of it. So you have different kinds of deep learning. You have stochastic deep learning, you have quantum deep learning, you have there is deep learning on the complex plane as well. So whatever deep learning we are doing, we are on the real world. If you go to TensorFlow or PyTorch platform, there is a separate section for complex optimization. So let's just leave it at that. I mean, so yeah.
Okay, moving on to the next question by Dia. People say AI will take over the world someday, and then we can see how ChatGPT can write codes, essays for us, but at the same time get simple mathematical facts wrong. What are your views on this? Even recently, I saw a post where someone did some easy addition. The answer was correct, but then the user said, "No, it's not 19, it's 21," and ChatGPT apologized that. Okay, so what are your views?
In that case, just like I said, right, it is at the end of the day, it is just a generative transformer, right? A generative transformer will try to generate based upon an important sampling. Trust me, it does not do any logic stuff. So if there is any misconception that the GPT is doing any logic stuff, that means adding towards something. No, absolutely not. It is not doing any addition stuff. What it is doing, it is looking up its knowledge base where there might have been 1 plus 2 somewhere in its knowledge base equal to 3, right? And then it is taking it up. So effectively it is nothing of that sort. I mean, it is just taking up from the knowledge base, and whatever instructions we say that it is not good, it is going to feedback loop that I showed. It is going to address that through the PPO policy back to the network, and that is how, it is just learning. So in that case, yeah.
Okay, so it's not doing the logical part, it's just okay. Uh, Next question by Deepak Ram. Can you suggest some websites or speakers should I follow to stay tuned with AI and ML developments? To stay in tune with the latest. Or like, is there a page which we can refer to stay in tune with the latest growth happening in AI or ML world or recent
Okay, so
projects?
yeah, there's certain blog posts. See, some of these. The reason why I'm taking some time to answer this is because based upon your mathematical aptitude, right? So if you want blogs which are mathematical, Sebastian for LLMs, for language models, I would say Sebastian Rudder is the person to go to. If you are interested in just open source layer abstraction, that means wrappers and everything, go to Hugging Face, and they have lots of blogs available on different resources. If by speakers, I don't know about any speakers as such. By speakers, I would recommend you follow people like Jan LeCun and everything, because they are the genuine speakers who give you, proper information. Follow MITs and everything, right? If you are interested, then go to MIT courses. Go understand about David Silver's reinforcement learning, right? I would say that. But if you are interested in learning about blogs, I would say Sebastian Rudder. Then there is one. I'm forgetting that name. I'm forgetting that name, but it is a very popular blog which posts about different complex algorithms, right? In machine learning. Plus, you have your Indian bloggers as well, right? You have AV Analytics Vidya. You have I recently took a session for them on diffusion models. So Analytics Vidya is one of them. Then you have Medium, right? Medium. Many beautiful people write beautiful pieces of stuff on there.
Yeah.
Medium is very good. So yeah, towards data science is also kind of fine. Yeah, follow these, like, based, I would say, not sticking to a particular speaker or a user. I would say to just Google it out, like, based upon what is your aptitude of learning, because everyone has a different aptitude of learning. So I cannot say that, go to him and go to him, go to hers, right? So if you are entirely mathematical, I would say go to Lillian Bank's blog, and try to understand what she has written in mathematics. Like, you need a pen and paper to understand what she has written, otherwise you will not understand. So that is why it is said, right? And I myself do not write any blogs, because I do not get much time to write blogs. I mainly write code. So if you're interested in code stuff, you will be finding me on GitHub, right? So just like I said, I don't write like blogs that much, because I honestly don't have that much time to sit and write. So yeah, so I hope that answers your question. It's a very abstract question, but I hope it gives you some insights. Just Google it out and see where you are trying to getting the best knowledge information from, which you can digest.
Absolutely. So hopefully that answers your question, Deepakram. Moving on to the next question by Sarah. There are many ML models available that we can use to train a data set. How do we decide which one to use in a problem? Mm.
I want to ask you, like, first, that means this particular question: how do you decide? How do we decide which one to use in our problem? That means the problem statement is not clear. Do not use machine learning where it is not meant to be used, right? If a problem can be solved by simple algorithms, right, use that. Do not, it is not a hard fast rule that you are trying to use machine learning algorithms for that. But yes, if you are, let's say you are trying to build uh, uh, let's say you are trying to do something like building classifiers and on, they're very cliche. Let's say you are trying to build a very simple use case of detecting animals in your computer vision camera. That is a problem statement. In that case, you need to understand your bounding box architecture, your camera configuration, what algorithm you are going to use, how will YOLO v4 or v5 be good or not. YOLO is a segmentation model. Okay, whether that will be good, or do I need to use any other segmentation models on that. So that is a use case. Okay, so before understanding the problem, try to think whether this problem requires CI, whether this problem requires me writing code through TensorFlow and PyTorch. It might sound fancy, right, for your clients and all, but at the end of the day, if it takes 2 seconds to write a code in simple graph algorithms, then why would I need to write a PyTorch layer on that,
Mm.
right? So understand your, and always when you are doing a problem, right, um, research on that problem before tackling it. Always research your problems. Okay, let's say you are trying to build a search engine. So when you are trying to build a search engine, do not go into building your let's say from the start only. If you're trying to say, no, I will build a knowledge graph and do all this stuff, and so you will not be able to do that. First, try to understand the basics of how a search engine works. Understand simple page rank algorithms. Those are not machine learning algorithms. Okay, learn about centrality methods, learn about eigenvalues and vectors. These are not machine learning based algorithms. These are simple stochastic statistical algorithms. Understand them, like whether this can be used, and then you see that I need to add more flavor to it. Then you go to the complex heavy stuff like graph neural networks and whatnot, right? So there so it is a very broad ended scope. Like, first, thoroughly research your problem which you want to solve. Take some time, like at least 2 weeks, to research your problem and see which pathway is it takes some time, and it takes experience to actually tackle a problem, and understand which is the there are many ways to solve a problem, but see which is the fastest way and which is the least effort, because we are lazy. Humans are lazy by default. So we need to have a solution which is fast, which is efficient for us, right?
Okay. I guess I'll have to start researching on the problems more when I write a Kaggle notebook. Because I used to straight away skip to EDA classification, and if I think, yeah,
No,
this
no,
can
no,
work,
no.
then I used to.
No. Just understand like what is the target. Because Kaggle notebooks is, well, there is a problem statement, right? In a Kaggle,
Hmm.
Kaggle is also beautiful. Kaggle, the different problem statements, but understand how you are going to solve that particular problem. Which model you are going to use. Model using is just if you are going to be a seasoned data scientist. I'm not a data scientist. Just to clarify, I am not a data scientist. I work in deep learning and distributed deep learning and very fine grained things, right? So I cannot disclose, but one of the black hole imagery that you have for NASA, right? We write custom kernels for that. So if you understand the level of skill that we are operating, so that is not data scientist. Data scientist means you give a problem statement. He will try out to first abstract as much data, metadata from the information or from the data as possible. That is the power of the data scientist, right? He will abstract whatever feature correlations, feature vectors, whatever there is, right? Disregard all other features that there is as a data scientist. Model is just 1 or 2 lines for him. 10% of
Uh,
the time he will just select wrappers, because the data scientist does not have time to try out. He has to deliver to his clients. That is the task of a data scientist. Machine learning engineers, deep learning engineers are separate. There is a fine distinction between them, but our industry does not follow that. But this is the fine thing, right? Your learning and writing models is just two lines of code. They will use PyTorch, TensorFlow to write simple lines of code on that. So testing models is nothing. They is abstracting from the data. Kaggle is for data scientists. Kaggle is also for deep learning engineers who are only interested. Like I myself write Kaggle notebooks only for the fun of writing, experimenting with different networks, like custom networks.
Hmm.
Right? I do not chase any data set. I do not chase anything. I just want to see performance analysis of my custom network. So yes, of course, Kaggle is a beautiful site. You can lots of resources, good people, doing great stuff there. I mean, yeah.
Okay. So, next question by Adi. Why are people talk? Why are people talking a lot about overfitting a model? How does it affect our models?
So, do you know what overfitting is? When you are talking about overfitting a model, I hope you know what overfitting is. Overfitting is an aspect of supervised learning, right? Supervised or semi-supervised. So, when you overfit a model, that means, in other words, in simple layman terms, when you test on unseen data set, it will fail. It will not give you that much of efficiency. By efficiency, I mean both in the terms of F1 recall, precision, and all this stuff. Okay, so model overfitting can be due to many things. I mean, depending upon the networks that you have, it can be due to your data set being very small. It can be due to your model being extremely large, so that the difference of the delta of the weights is not getting properly passed to the layer zero or the initial layers. It is not getting properly flowed. Like, it is getting a bottleneck kind of it is going like a backward funnel. So your weights at the front layer zero is not getting updated that much. So your model is not training. Your training loss is static. So this is so there are different ways to alleviate that as well, to remove those. Just change your different layers, try different combinations, build custom kernels for that. Custom kernels means try to add different framework layers like Torch or TensorFlow layers, or try to remove them. Try to build certain different um, you know mathematical computations. Like ResNet was actually built on top of your standard model, confidence model, because of overfitting, just to avoid overfitting. So ResNet is nothing but the residual part of the network is nothing but an addition or a concatenation. Nothing that is a bypass way. So that is what it is. What is there? So it affects our models to a grade, because you are training it on, but your accuracy will not improve. Your precision metrics will not improve. So it is good to investigate more into the data, more into the model. So yeah, it is a very open-ended answer. There is no proper answer for this. Changing your models is the secondary way. The first is getting to know the data better. Maybe your feature selection is wrong. So yeah.
Yeah. So, thank you so much for answering all our queries. It was a fun Q&A session. I don't, due to time constraint, we won't be able to take any more questions for now. Apologies on our behalf. And thank you so much, sir, for having such a great session today. And so giving us so much knowledge. There are so many things to learn. I'll probably visit the session again to, you know, learn to clear my concepts and get a tight grasp on ChatGPT as well. And once again, I would like to thank you for your time and knowledge, and it was a really good session.
Thank you everyone for having me, and thank you. It was a beautiful session. So
So,
hope to see you guys soon, and all the best for your future careers. Right, do good, and if you are in the core branches, do not get bogged down by all this code stuff. Right, if you are good in core, if just learn your if you are in mechanical, chemical, and whatnot, this, right. If you are in
mm,
electrical, understand, study powered electronics, very good. If you are in mechanical, just understand IC engines. And if you want to go into the automobile field, everywhere there is good scope of softwares and things, right. So I know a few aspects of different branches, so that is why I wanted to highlight that there is no need to worry right. So different organizations are there. We have different flexibilities to learn different aspects. So yeah, thank you.
thank you. With this, we'll end our session.